this video we're going to be doing the logarithmic function. So, to jump right into it, in the past we have done the exponential function y equals a to the power of x. So y equals a to the power of x. Let's say this is a 1 on the y-axis. We have an asymptote, that is this axis. So this will forever go like that, cross 1, and forever go like that. This line right here is our y equals a to the power of x. Now, the logarithmic function, let me introduce you to y equals log a of x. So, when we look at this function here, there's a couple things to note. This little a here, which is small, like it's supposed to be written like this, log a small a little lower, and then a value x. Usually when you see this log, say a number or a variable, say a variable, or let's say a number of 5, you don't see it here, but this is actually by default set to 10, unless otherwise stated, the a value. So let's note one thing down from the start, the inverse of the exponential function y equals a to the power of x, which you can also write as, let me use the other one, x is equal to a to the power of y, and the equivalent form of that would be to write y is equal to log a of x. So let's write that down somewhere. X equals a to the power of y translates to y equals log a log ax. One thing to note is that these two functions are actually inverse of them. So if we go back to our knowledge on inverse functions, remember, if we draw an imaginary line at y equals x, then we can make a reflection of the function on this axis, and that will give us our inverse function. So in this case, it will be like this. And that is our logarithmic function. So that's how it looks. Maybe we can look a little more into what it actually means. Let me write that down here somewhere. So since we know x equals a to the power of y, and y equals log a to the x, log base a of x is, they are equivalent to each other, we can say that a logarithmic logarithm is an exponent. The expression itself, say log ax, this means that the exponent that must be applied to base a to get this value of x. So, if that didn't make sense, this will, say we have, log 2 of 8 is equal to 3. So we know that 2 to the power of 3 is equal to 8. So what I was saying before is that this expression is basically giving you the exponent 3, which is here. 2 to the power of 3, 3 is the exponent here. This expression gives you whatever this equates to. When you punch it into a calculator, it gives you the exponent. If you punch in this into a calculator, you'll get 3. And what that tells you is that that number 3 is what you need to apply as an exponent to your base, which is 2, to get x, in this case, is 8. Okay, so now that we have, I want to say, a very straightforward introduction, I do want to also cover the function transformations for this particular function. So let's write out the full. Let's say we have a function of x. This is the full and there you have it. So these values that you see here are not much different than when we were doing transformations to the parabolic functions, or parabola, or quadratics. So we know that a gives you a vertical stretch or compression, and you know that if it is a negative, that means that it flips on the x-axis. Let's do k next. You know that k is actually going to give you the horizontal and you know that if it is negative, then there is a reflection on the y-axis, and you already know D and C. D gives you the horizontal that's the right word, base 10 of x. But what if we applied a factor of 2? That would actually stretch it in the vertical stretch, and then so whatever, say this would go here, this would go here, this would go there. So everything would just get stretched by a factor of 2. So you'd have, so like that would go there, that would go there, but this is still there. I'm only applying the 2, but then you have the negative 2, so you just flip that over, like so. Trying to get these points. So that gives us the negative 2, and then we also have x minus 4, which means if that's 1, that's 2, 3, 4. I'm sorry for the mess, but and that is our y equals negative 2 log 10 x minus 4. And you know we went x minus 4, we went over to the right side because the formula is x minus, I think it was c or d, I forget. But yeah, you're subtracting the horizontal translation, so since we have x minus 4, we're subtracting a positive 4. If this said x plus 4, then we would be interpreting it as this and moving over to the other side. And I think that pretty much wraps the whatever we can do with this function. You really only need an intro to this function. You don't need to know too much about it right now. One thing you can do in your spare time is look up or try to figure out, if you can on your own, the domain and range for this function. And if you can do that and put it in the comment section, then you win my utmost respect. But for now, I'm going to say that's all for this video, and I shall see you in the next one. Okay, so in this video we're going to be evaluating logarithms. So by that I mean we're going to look at what we learned in our last video log, where I showed you that we had y equals log a to the x is the same as saying x equals a to the y. So keeping this in mind, let's solve for this. If we have log 464 equals x, if we were to rearrange this, we know that the base, I want to solve for x here. I know that I have to take, well, by definition, the log function, this logarithm is an exponent. The exponent of what this whole thing, which is equal to x. So 4 to x should give me 64. And that is how you rearrange the exponent into log form and back and forth. x. So it's from here it's quite straightforward. 4 to the x is equal to 4 to the 3, so x equals 3. And this is because I know 4 times 4 equals 16 times 4 is equal to 64. No magic there. Just good old intuition. Okay. Let's do another one. Let's do log, say, base 3, 1 over 27 is equal to x. So, same formula. 3 to the power of x is equal to 1 over 27. I don't need that. And yeah. Let's see. I know 27 is equal to 3 cubed. 3 times 3 equals 9. 9 times 3 is equal to 27. I know that. So I can write which is the same as saying, bringing that to the numerator is just writing that. So I can say x is equal to negative 3. And there you have it. Sorcery at work. So, I wonder what else we can do. Let's do log 5 root 3 of 25 equals to x. This is going to be much more interesting, but not really. 5 to the power of x, or base to the power of the entire exponent, which is equal to x, will give us this value, root 3 of 25. So, 25 is actually 5 squared, and root 3 of something is actually x to the 1 over 3. So if I have root 3 of that, let me write that here. If I have root 3 of 5 squared, that's basically saying 5 to the power of 2 times 1 over 3, which is also 5 to the power of 2 over 3. And that means x is equal to 5 to the... Sorry. Confusing myself again. 2 over 3. And what looks scary in the beginning is now not. And we can also look at, let's touch up on the log tens. So it's important to know this this is so important. If you actually punch into your calculator, I don't know which kind of calculator you might have, but by default, if you push the log button and whatever number like you put in right after that, it's going to give it to you in log 10. And you can actually check that by punching that into your calculator, because if you push in log 10 and it's going to default at this, you should get 1. Because if you do that, 10 to the x is equal to 10. What to the power? Sorry, 10 to the power of what gives you 10? Only that. To the power of 1 will give you that. And same with if you decided to do not just 10. Say you decided to do 100. Then you would get what? 10 to the x is equal to 100. So what? It has to be 10 to the 2 equals 100. So x is equal to 2. So if you put this into your calculator, log 100, you should get 2. So let's continue with that. Let's see some other. Am I missing any special cases that we should touch upon before we move on? Let's see, log 6 to the 1 equals to x. Let's see. So let's put that into here, equals 1. Okay, so 6 to the power of what will give me 1? Well, obviously 6 to the power of 0 will give me 1, because anything to the power of 0 is equal to 1. Remember that. So if you ever put a 1 in there, just know you're gonna get a 0, even on the calculator. Let's do another one. Let's do now this one might look confusing to you, but let's just try, instead of putting in x, let's put in a y and see what we get. 5 to the power of y is equal to 5 to the power of x, which means y is equal to x. Well, there you go. Let's do one more. All these unique cases that we can actually run into. Just so you're prepared, let's do 6 to the power of log 6x base 6 value x. And let's say we equate this to y. So, how do we do this? We just rearrange this by looking at here. We're gonna take this and go into that form. So this term will become, right now, let me rearrange this for you so you can see. Look at this one. x equals a to the y, but in this case we have y is equal to 6 log base 6x. But that's our y, so that's going to become here. So that'll become log 6x, which is that. I'm sorry, this exponent now became this. That's here. And now I'm going to have my log a, which is the 6 here, this big one, and then x. Sorry, in uppercase. That was a y here. So that x is coming from here. So for my case, y is coming from there. So now I have these two, and obviously log 6x equals log base 6y, which means x is equal to y. Again, you might think that we didn't really actually do anything to this, but more times than others, you're really just proving things. So, congratulations on proving this. I'm proud of you. And if you want some homework, here you go. Evaluate this. Log base 3 to the 5. Log, the base is 3, and the value here is 3 to the power of 5. Evaluate this and put it in the comments below. And that's all for this video, and I shall see you in the next one. Okay, so in today's video we're going to be looking at the laws of logarithms. So there really is only a few that you need to know. I'm just going to quickly give them to you before we just dive into some examples. We're going to look first at the product law, which basically states that if you have a log with a base a and you have x times y, that is the same as saying log base a x plus log base a y. So this is an identity. Similarly, we also have a quotient law. So if you have a log with the base a and you have x over y, that is also the same as saying log base a x minus log base a y. And the final one is going to be our power law, which basically states if you have a log base a with x to the power of r, that is the same as saying r log a to the power of x, which basically means you brought down the r. So I would highly advise that everybody, wrap their heads around this. It's a really good thing to, keep in mind. So let's see if we can actually do some examples with these. Let's say we have log base 3, 6, plus log base 3, 4.5. And I tell you, go ahead, evaluate this, give me what it is. We know that from our product law, that, log a xy is equal to log a x plus log a y, and we have that here and here, so we can easily just put it into this form. So let's go ahead and do that, because we have the same base. So we have log 3, 6 times 4.5, and that is equal to log 3. 6 times 4.5 should be 27. And we know what the answer to that is. If log 3, 27 is equal to x, then 3 to the power of x is equal to 27. And we know that x has to be 3, because that's what gives us, so x is equal to 3. And see how easy math just became. So let's do another one. This time let's do a subtraction. And you already know I'm going to tell you that log a x minus log a y is equal to log a x over y, because of our quotient rule, our quotient law, sorry. So we have the 2, and let's do our dividing, because we're so efficient with math. Now that we can quickly do this on the fly, which means I have log base 2 times 16, and I know that 2 to the x should give me 16, so I guess that's 2 times 2 is 4, times 2 is 8, times 2 is 16, so x equals 4. I should have been able to do that quicker in my head. Anywho, let's do log base 5, 3 to the, base 5, cube root 3, 25. So, if you remember you can see the pattern where I'm going with this one. If you have log base a x to the r, you can write that as r log a to the power, to the value of x. You might be wondering, what's our r? Well, actually, this we can rewrite as log 5, 25 to the 1 over 3. So, let's rewrite that over here, 1 over 3, log 5, 25. Now this expression here, log 5, 25, that should give me, that alone should give me 5 to the x equals 25. And really, that's honestly how easy math is. I would not stress too much about it. So far, we've only done easy things. Let's actually do something a little more messed up. Let's do this. Let's say I have this log a x cubed y squared over w. And now I want to represent this in terms of log ax, log ay, and log aw. So let's start doing this. I want to basically disassemble this entire thing and rewrite it in terms of 1, 2, and 3. So the first thing I'm going to do is take this exponent here, log a, and then x cubed y squared over w to the power of 1 over 2. And now that I have that, I can move that down using our product law, which is log a x cubed y squared over w. And also, now we can use our quotient rule to now split that. If you remember our quotient rule, if you have a division, you can convert this into a subtraction. And then we have this multiplication. You remember our multiplication, we can change this to and now down here, if I have space, I can bring out 1 over 2. Remember our power rule for each one of these. Well, for these two, we can do 3 log a x cubed plus 2 log a y. Oh, sorry. I don't know why I'm putting that again. And there we have that. So now I can actually bring this into here and rewrite this. Multiply this, like open the bracket up. So I can write 1 over 2 for this one. This one would just be 1 because it'd be 2 over 2. So I can write like that. And our first one would become 3 over 2. And there we have our end result from this all the way to this. And we can actually even work backwards to come up with the this one, I'll leave you with a parting gift. Maybe, let's see. Evaluate that one. Maybe even you can do, let's see. So that's 1, that's 2. That's log base 2 of 224 and minus log base 2 of 7. So that's all for this video, and I shall see you in the next one. Okay, so in this video we're going to be solving exponential equations. So let's say we have a 200 gram of something radioactive called radon, and 16 days later only 12.5 grams remained. So the question is, what is the half-life? So what is the half-life? Let's calculate that. Well, first let's start writing our half-life formula, which we know is our principal, right? Times 1 over 2, which represents half-life, t over h, t being the number of days, the time that has passed, and h being the half-life. So let's plug in what we have. M of t is what remains. We started with 200 grams, and we're left with, I'm going to write this as 0.5 instead. And we know that 16 days has passed, and h is what we're trying to find, the half-life. So let's start solving for h. So first thing I'm going to do is give myself some space here. Let me just write that up there. So if I divide both sides by 200, 12.5 over 200 should give me 0.0625. And I'm left with that. Now what we're going to do that we haven't done before is now apply the logarithm. We're going to apply the logarithm. I'm not saying it's correct. We're going to log both sides. Because right now, from a mathematical standpoint, this side is equal to this side. For a fact, we know that to be true because of this formula, which we are reinforcing. Which means that if I take the log of both sides, I should get the same number as well. And like taking the log of something is always useful, because now I have this exponent up here, which I can use the power law to bring that down here to 16 over h log 0.5 equal to the side still 0.0625. And is isolate this, and well, I can multiply both sides by this h, and this will cancel out, and I'll be left with that. Which means I can divide both sides by this log 0.0625, and I'll be left with 16 log 0.5 over log 0.0625, which, if you put into the calculator, you get 4. So the half-life is going to be 4. So yeah, let's move on to another example. Let's do this. 2 to the power of x plus 2 minus 2 to the power of x is equal to 24. So, what can we do here? If we remember our exponential laws, we know that when you have 2 to the power of x times 2 to the power of, say, 2, when you multiply these two, the exponents actually add. So that's how we're going to split this one here. 2 to the power of x times 2 to the power of 2 minus 2 to the power of x is equal to 24. Now I'm going to factor out 2 to the x from this side, and I'm left with 2 squared minus 1 is equal to 24. Now I can just solve for x, which being, 2 to the power of x is equal to 2 squared is 4 minus 1 is 3. I can just divide that side by 3, which should give me 8. And I know 2 to the x is equal to 2 to the 3. X is equal to 3. Easy peasy lemon squeezy. Now, to do or not to do another word problem. Yeah, let's do it. Let's say we have an investment of 2,500. Let's say you want it to grow at a rate of 4.8%, compounded annually. The question is, how long till it becomes 4,000? So let's put that into our formula. A equals principal times 1 plus interest to the power of n. We know that we want 4,000, and we start with 2,000. 4.8 is actually 0.048 to the power of n. So, let's start solving this. We have, 2,000 on one side, 4,000 the other. Divide that, 4,000 over 2,000. Should be left with this. Oh wait, my mistake. It's 2,500. So it should be 4,000. It should be, 4,000 over 2,500 should be 1.6. this log 1.048, so I'm left with log 1.6, log 1.048, and you punch this into the calculator, you should get 10.025, and that's how many years it will take if you have 2,500 invested, compounding annually to at 4.8% to get $4,000. You know, math being used in the real world. Let's do one more. Let's do this. 2 to the power of x plus 1 is equal to 3 to the power of x minus 1. And let's try solving this. Try to find the exact value of this. So let's start by taking the log of both sides because I want to bring these exponents out to play. So, using the power rule, I'm going to bring this x plus 1 out here. So I should be left with log 2, and same on this side, x minus 1. I should be left with a log 3. So, let's go ahead and expand both sides. So I should have x log 2 plus log 2 equals x log 3 minus log 3. And now let's arrange the x's on one side and the non-x's on the other side. So I should have, I'll bring this 3 over to that side. So I'll have log 3 plus log 2, and I'll bring that guy over to this side, x log 3 minus x log 2. And what I'll do is divide. See, now I can actually factor out an x from this side, like so. So I'll be left with log 2. So now I have x here, I can really just do this. X is equal to what is on this side, log 3 plus log 2 divided by what was here, log 3 minus log 2. And there you go. I've successfully taken out the x out of there by bringing them out, expanding, moving them to one side, factoring it out, and isolating it. I have x by itself, and I can punch these into the calculator and get about 4.42. That may have looked complicated, but you know, take your time with it. Practice. Always try to isolate. Try to look for ways to isolate x on its own. And yeah, the solution will come. Anyways, that was fun. I guess if you want to try one on your own, let's see what I got. You can do this video, and I shall see you in the next one. Okay, so in this video we're going to be solving logarithmic equations. So let's start with an example. Say we have log x 0.04 is equal to negative 2. So let's rewrite this in the way that we know. We know that the base to the power of this is equal to that. And so what is that going to give us? One thing to identify here is that 0.04 is actually 1 over 25. So let's start writing this in the similar way. I know that x to the negative 2 is also equal to 1 over 5 squared, which is also x to the negative 2 is also equal to 5 to the negative 2, which means x is equal to 5. See? Easy peasy. Let's try something like this. Say we have log base 7 3x minus 5 equals log base 7 16. One thing to note here, maybe this is probably a new law that I haven't shown you before, but if you have a log of a and say something here, m, and then you have a log with the same base and n, if this is your equation, which we're looking at similarly here, if you have log base a of something equaling log base a of another thing, we can say m is equal to n. That holds true in math. So in this case, same log base. So we can write 3x minus 5 is equal to 16. And then this is just simple algebra. I know that looks scary, but once you apply rules, then you have a cheat code. So let's do another one. Let's say we have log base 2 30x minus log base 2 5 equals log base 2 12. So let's approach this with I see a subtraction that could give me my log base 2 30x over 5, my quotient law, equals log 2 12. So this will be log 2 6x, because I divided it by 5, equals to log 2 12. And remember what we said, we can easily just say 6x equals 12 because of our if you remember our addition formula, then you remember that we have, our product law. You remember we can do this, remember log. That's our product law. So according to that, we can write log x times x squared equals to 12, which is log x cubed equals to 12. As you can see, I haven't written a base here, which means by default it's 10. So let's rewrite this as 10 to the power of 12 equals to x cubed. So, how are we gonna solve this? I mean, we could punch it into a calculator, just cube root both sides. That should give us x is equal to, well, we don't exactly need to, because this value here, 10 to the 12, if you do the correct algebra on it, you can just do 10 to the 4, which is 10,000. So we have x is equal to 10,000. Yeah, that's correct. Okay. Let's try doing another one. One last one. Before we wrap this series up, say we have log 2x plus 3 plus log 2x minus 3 equals 4. Now, let's approach this with all of our knowledge of logarithmic expressions and equations and the laws. So I see I'm adding 2 logs here, so I can actually turn that into the product law. X plus 3, x minus 3 equals 4, which means I have, if I expand that, I'll have x squared. That looks like a difference of cubes, so x minus 3x plus 3x will cancel out, and I'll be left with 3 times 3 is 9. Oh, I forgot to write my base. And now that we're here, we can write we can convert this equation into an exponent form. 2 to the power of 4 is equal to that. Let me write a little more up. 2 to the 4 is equal to x squared minus 9. So now I am here. I want to solve that, but that looks like it's just simple math. 2 to the 4 is, so x squared minus 9 is equal to 2 to the 4 the square root of that, I can actually get 2. I can get x equals 5, or I can get x is equal to negative 5. So I can just write, x is equal to plus or minus 5. And that is how we do the math. Well, that is going to be all for this video in terms of checking. If you want to do one, I can give you one to do and see if you get it. Match it with other people if you want. Try solving this one. These are both bases of 5, and that's a 36. Yeah. Good luck, and post your answer in the comments section, and this concludes our grade 12 function series, and I shall see you in whatever we do next.